Imagine for a second that you could design a brand new revolutionary material, not in a lab with all the glass speakers and complicated equipment, but entirely inside a computer. Well, today we're diving into exactly that, how scientists are literally creating super materials from the atom up, all thanks to the power of simulation. So let's start with a pretty wild idea. What if you could invent the perfect material for any job you could think of? Maybe a crazy efficient solar panel or a computer chip that cools itself, by building and testing it virtually, atom by atom, before a single piece of it exists in the real world. This isn't science fiction anymore. This is the incredible promise of computational materials science, and it is changing the game. So what's the big deal? Why are we on this constant, relentless search for new materials? Well, it's pretty simple. Our entire technological world is built on them. Just think about it for a second. Every single leap forward in technology, whether it's a faster phone in your pocket or a more powerful satellite orbiting the Earth, totally depends on us finding new materials with unique new abilities. The research we're digging into today is zeroing in on two super important areas: magnetic and thermoelectric materials. These really are the building blocks for what comes next. All right, let's meet the stars of our show today. We're talking about two chemical compounds that, honestly, have been flying under the radar from a theoretical standpoint: KAlTe₂ and KInTe₂. So what you're looking at here, these aren't photos. Think of them as the atomic blueprints for our two materials. On the left, you've got KAlTe₂, and on the right, KInTe₂. And it's their very specific arrangement, this unique crystal structure, that is the secret sauce to all the amazing properties they're predicted to have. Now, the name ternary telluride probably sounds super complicated, right? But it's actually just a recipe. Ternary just means it has three main ingredients, and telluride tells you one of them is tellurium. The formula is just AbX2, where A is potassium, B is either aluminum or indium, and X, well, that's our tellurium. Simple as that. Okay, so you've got this blueprint on a computer, but how in the world do you test a material that isn't even real yet? Simple. You build a virtual laboratory that runs on the fundamental laws of physics. The secret weapon behind all of this is something called density functional theory, or DFT for short. The best way to think about it is like a superpowered digital microscope. But instead of looking at tiny cells, it zooms in on a material's atoms and uses the rules of quantum mechanics to predict exactly how its electrons are going to behave. And from that, you can figure out pretty much every property the material will have. It's incredible. The whole process is actually pretty straightforward when you break it down. First, you build that atomic blueprint we saw. Second, you let a supercomputer run a DFT simulation, basically letting the laws of physics do their thing. And finally, you just analyze the data that comes out to see what kind of amazing properties your new virtual material has. So, they ran the simulations. What did they find out? What's the big secret that makes these two materials so special? I know. This graph looks a little intimidating, but stick with me, because it tells us something absolutely crucial. It's showing the electronic band structure. That empty space between the lower colored lines and the upper ones, that's called the band gap. And for an electron to conduct electricity, it has to make that jump. The size and nature of that gap, well, that's everything. And here's why that little detail is a huge deal. The simulation predicted that both of these materials have something called a direct band gap. All that means is that electrons can jump across that gap really, really efficiently. This is an incredible property for anything that needs to turn electricity into light or light back into electricity. We're talking next-gen LEDs and super efficient solar cells. But that's not all. The simulation also gave us a peek into their magnetic personalities. It turns out KAlTe₂ is paramagnetic, meaning its atoms will kind of weakly line up with a magnetic field. KInTe₂, on the other hand, is diamagnetic. It actually pushes back against a magnetic field. Now, they're both pretty weak magnets, but having these distinct properties could be super useful for sensitive electronics where you need precise magnetic control. Okay, their optical and magnetic futures are cool for sure, but the real headline grabber, the discovery that gets scientists really excited, is how these materials handle energy. Specifically, their mind-blowing potential to take waste heat, one of the biggest untapped energy sources on the entire planet, and turn it directly into electricity. This is all possible because of something called the thermoelectric effect. It's basically magic. You heat up one side of a special material and keep the other side cool, and the electrons inside just start moving, creating an electrical voltage. It's like a solid-state engine with zero moving parts, grabbing wasted heat from a car's exhaust or a factory and turning it into free power. So how good are they at this? Well, just take a look at this graph. Do you see that crazy sharp peak for KAlTe₂? That's not just a good sign. That is the simulation practically screaming at us that this material generates a massive voltage from even a tiny temperature difference. This is a spectacular result. To really put a final score on it, scientists use a single metric called the figure of merit, or just ZT. You can think of it as the ultimate report card. It combines all the important factors into one number to grade just how good a material is at this heat to electricity conversion. And here's the number you need to remember: 1. For material to be considered a serious, top-tier candidate for real-world devices, its ZT value needs to hit at least 1.0. That's the gold standard. So the big question is, how did our virtual materials do? All right, let's start with KAlTe₂. The result? A peak ZT value of 0.99. Wow! I mean, that is unbelievably close. It is literally knocking on the door of being a high-performance material, an absolutely exceptional candidate. But can its sibling do even better? And what about KInTe₂? The simulation predicts a peak ZT value of 1.1. It did it! It broke the barrier. This is that moment of discovery. This single calculation identifies KInTe₂ as a truly high-potential material for turning waste heat into power. And this breakthrough was found entirely inside a computer. How cool is that? So here it is, our tale of the tellurides, all summed up. You have KAlTe₂ with its wider band gap, coming in at an incredible ZT of 0.99. And then you have KInTe₂ with a narrower gap, which just smashes through that high-performance line to hit 1.1, all while they both show their own distinct magnetic behaviors. So what's the bottom line here? The key takeaway is crystal clear. By using these incredibly powerful theoretical tools, researchers have pinpointed two brand new compounds with huge promise. They've essentially handed experimental scientists a detailed treasure map, telling them exactly what to build and what amazing properties they should expect to find. And this really just leaves us with one final thought. If we can discover high-performance energy materials this way, what's next? Could we design materials to create clean water for everyone? Or to build better batteries? Maybe even to power quantum computers. The era of designing supermaterials from the atom up, inside a computer, is officially here. And you know what? It's just getting started.